All right, morning everyone. How we doing this morning? Sorry about the little bit delayed start. My camera mount officially broke and I had to go find one this morning. So here we are. I think this is a little better. Found some new tricks and techniques to help see it better. People were saying in the video that it was hard to see or whatever. I'm still trying to work out a way for me to write and you guys to see, but that's an evolving process. Test. Thank you for everyone who took the test. Hopefully it went over with not too many glitches. I know there was one issue with the honors test, but I fixed it in test and texted everybody. You can check your scores are online on School Tool. Put them there yesterday. Averages were decent, so I think we're going to leave them straight up as that. Next week is technically spring break, and I'm sure most of you have heard at this point in time that the governor or state ed has said that we do have to continue teaching. I normally do 3 lessons a week. I'm going to do a lesson on Monday and Wednesday. I think Monday I'm going to give you a lab that'll be due the following Monday. It's just a lab of Half-Life Lab. You'll need to acquire, I think 50, I think is the number I'm going to use, 50 pennies or 50 coins, 50 M&Ms that have M's on one side and nothing on the other, or 50 Skittles, with an S on one side and the other. Basically something you can flip. All right, so you can technically use cereal pieces if you have like frosted mini or frosted shredded wheat. It's got the frosting on one side, not on the other. Something that you can flip back and forth. But I'll talk more about that on Monday. Today we're going to start a unit on radiation. Normally on this day I do have a couple little videos that I do show in class. I'm going to give you the links of those in Google Classroom to watch. A couple of them are very good. The most radioactive places on the planet is one that you're going to want to take some notes on, because I do refer to that throughout the unit. So definitely watch that one and take some notes. There's one on Marie Curie. We'll talk about her in a minute. That if you want to watch, you're welcome to. And then the other ones just show how it's kind of used in different ways and aspects. But definitely the most radioactive places is definitely the most important video out of them all. The workbook, I'm going to give it to you electronically. I have no way of getting you hard copies of it. Here's where we're going to start to evolve into issues if you don't have a printer. It's going to require more writing for you for today. You cannot just write down the answer for next class, or you'll see that you'll have to write down a particle or a nuclear particle. You're going to have to write the whole reaction, which is fine. It's good practice for you. But if you do have a printer available, then you can just print the sheet and fill in the blanks on the reactions on the sheets. All right. And I'm going to recommend that when you do submit them to Google Classroom, please use the scan function. If you have an iPhone, go into Notes and basically take a picture on the camera, and one of the options is scan as a PDF. It works way better. The picture, the writing's much clearer, and it submits as one document versus multiple documents, which is easier for Google Classroom to handle. If you have an Android phone, you have a feature. If you've downloaded the Google Drive app, when you go into Google Drive, if you click on picture, it'll automatically scan it as a PDF. So that's kind of the Android's way of dealing with it. And then the iPhone way is to go into Notes. Much easier for you. You can scan it and you can send it in as all as one document. It's easier for me to see and read as well. So, it's a win-win for both sides. Okay. All right. So let's get right to our bell ringer today. Oh, I got a reflection on here. The black's going to be a reflection. Hey guys, if you can see me in the reflection. Radiation. We're starting a unit with radiation. I try to kind of see what you guys know about radiation with this bell ringer. Obviously, I can't get interaction back from you. A lot of people think radiation is bad. Some radiation is bad. Something called ionizing radiation, that's bad for us. But, you're being bombarded with radiation right now, whether it's sound radiation, light radiation. There's just natural radiation in the atmosphere and in the buildings you live. Some buildings have more based on the materials that they were built with. But radiation, all radiation is energy waves. All right. How much energy they have will determine if it's harmful for you or not. Radio waves, sound waves, light waves, those aren't really that bad. They are energy. All right, you guys are on your cell phones all the time. That's energy. It's electromagnetic radiation. It's when you get up into the higher radiation forms, gamma rays. You probably have heard of X-rays to some extent if you did it all the time. Then you get into ultraviolet and things like that. That's where it gets to become dangerous. That's called what's called ionizing radiation, where it creates ions in your body, or specifically in your cells, and it can cause some damage to some certain types of cells in your body. And we'll talk about that as we go through the unit. All right, but radiation, a lot of people think it's bad. Not necessarily bad, just when it's that ionizing form, which in the normal everyday life, most people aren't exposed to ionizing radiation, so it's not an issue. All right. Nuclear chemistry. This unit, like I told you guys before we left, is a pretty easy unit. That's why I chose to do it while we were out. People have asked me questions, when are we coming back? To be honest, I have no idea. It's an evolving process. My expectation is we won't be back at least until May. And that's, I think, a best case scenario. But anyways, this is something we do pretty easily, virtually like this. How's it used? It's used to make electricity. You've seen that top left picture up here. That's an actual picture of the nuclear power plant up in Oswego. All right, some people are familiar with it. If you've been out on the water in Oswego, you see this thing right here with the big white smoke coming out of the top. That white smoke is just water vapor. So that's actually a clean material coming out of that. That's called the cooling tower. Like I've said in class a couple times, this is close enough that if there were to be like a Chernobyl type incident there, it would impact us here. But it is generally a pretty safe way to manufacture electricity. We'll talk about the storage of the waste after, later on in the unit. So that's one way. Food is another way. So you can see right here, food, strawberries, lots of vegetables are irradiated to basically kill any pathogens that are on them, viruses, bacteria, mold. In some fruits or vegetables, it's to prevent them from sprouting, like potatoes. If you've ever had potatoes, you leave them in your cupboard or in the drawer for a long time, they might start growing a plant. If it's been irradiated, that limits that ability to do that. There's no lasting long-term effect of the exposure to radiation. It's just that it would kill anything that's living on the strawberries. The strawberries themselves at this point in time are dead, so the radiation is not going to have anything to do with those. Radiation only impacts rapidly dividing cells, and we'll talk about that as we go through. Up here, medical, there's many medical forms of it. This is a simple x-ray. If you've had CAT scans, you've had GIs or upper GIs or lower GIs or any endoscope's not really nuclear, but upper GIs and lower GIs. Upper GIs, if you've ever had to drink that liquid and then get an image taken, that's using radiation. And that radiation is going to have something that's going to be quickly removed from your body, and it's going to have a relatively short half-life. You should have these in your house. These do have radiation in them. All right, there's a radioactive source called americium-121. Every smoke detector is built the same way, and it sends that particle. It sends I believe it's an alpha particle. I'd have to look it up. It sends an alpha particle beam, and when that beam gets interrupted by smoke is when it makes that noise. So that's how smoke detectors work. You're not impacted by the radiation given off by them, even if you just stand underneath them for hundreds of years. It's not enough or a type of radiation that can cause any damage to humans. So there's lots of ways nuclear chemistry is used, and I try to give you some examples of places where it's not normally done or where you would normally think of it. All right, Marie Curie, one of the biggest female scientists, or first female scientists, and she actually discovered radioactivity back in late 1800s, early 1900s. She worked with her husband, who died fairly young. She survived longer. A lot of people think that he died from radiation exposure. He actually died in, I think it was a horse and buggy accident. She ultimately died from complications from exposure to radiation. But you can see that she lived to, let's see, that's 24 and 34, so that's 58. That's a pretty long lifespan at that time frame when she lived. So there's a video that I'm going to show you. It's a mini biography on here, and I would recommend that you watch that one because it does go into some of the, how radiation was discovered, and some things into her lab. So it's kind of cool. So that with the one with the most radioactive places on the planet are the two videos that I would highly recommend for you to watch, and that's why I'm going to put them on Google Classroom. Why is a particular nuclide or isotope in development stable or unstable? So this is where we talk about radiation deals with the nucleus. Or nuclear chemistry deals with chemistry of the nucleus. Up until now, we've dealt with chemistry dealing with electrons being shared, transferred to get to what's called a stable octet. We haven't talked anything about the nucleus. All right, nuclear chemistry deals with that, and things that are going to give off radioactive particles are things that have unstable nuclei or an unstable nuclides, if we say the simple or the singular form. All right, the answer is related to whether, if a nucleus is stable or not, has to do with the ratio of protons and neutrons. And those are obviously found within the nucleus. We do know that. I'm going to pop up a graph here, I think. I don't know if it's this slide or the next slide. But what happens is when something's radioactive, the nucleus is unstable, and it's going to decompose or break down and to turn into something that's more stable. It actually changes from one element into other elements. All right, and that's actually the process of radioactive decay. All right, I think it must be the next slide. And radioactive decay is an attempt to correct the ratio of protons and neutrons. The ratio that's stable is close to 1-to-1, 1 proton to 1 neutron. Sometimes when they decay into another radioactive nucleus. So that then has to decay into another nucleus that may be stable or maybe not be stable. And that's the issue with nuclear reactors. You take a radioactive nucleus, it will decay, but it's going to decay into another nucleus that is unstable. And then that nucleus is going to remain unstable for, hundreds to thousands of years, depending on what it was. And we have to store that radioactive material. So that's kind of one of the problems with nuclear sourcing of energy. All right, but all radioactive decay, another term for radioactive decay is transmutation. I'll talk about that later. It's changing one element into another, or more specifically, one nucleus into another. So here's that graph that I was talking about. If you're to graph all the known atoms that we know of, so if you look down here, this is the number of protons. All right, so this is the number of protons versus the number of neutrons. And you can see that some elements have many isotopes. Remember, isotopes, same proton, different neutron. So they have different isotopes. So as you get up here where there's bigger elements or bigger nuclei, they have more isotopes. Down here, they have 1, 2, or 3 isotopes. All right, up here you can get into many isotopes. And there's something about, you can predict whether it's an alpha emitter or beta emitter. We don't get into that at all. But all that's drawn in on here is this line right here represents 1-to-1. It's called a band of stability. All right, down in the lower elements, most elements are stable, or a lot of elements are stable, or some of them, or at least one isotope of the element is stable. You can see down here. As you get up here, you can see that there's no little dot near the line. So that means there's no isotope of these elements that are stable. So that's where this thing comes from. All atoms above atomic number 82 are unstable. And if you remember 82, we talked about this before. I'll put this up here. 82 is right here. If you remember, PB is lead. So lead is the last element on the periodic table to have a stable isotope. Every element 83 and above has no known stable isotope, so they are all radioactive, so they're all going to decay into something else. Eventually they'll decay into an atom that is stable, so they'll get to an atom that is that's 82 or below. All right, but sometimes that's a one-step or other times it takes 3, 4, 5 decay series to do that. But this just shows you that 1-to-1, and you can see down in the lower ends, all right, what can happen with that. All right. Here we go, types of nuclear particles. And for Regents kids, I don't know if there's a difference anymore between Regents and non-Regents. And I know people have asked that question. I got word that there's a meeting at the state level Monday where the Board of Regents is talking to decide what's happening with the Regents. So hopefully sometime beginning of next week, we will get an answer to that. But this table, many of these particles on this tape, this graph that I'm gonna show right here, are on this reference table right here, table O. We're gonna use table O in this unit, and we're gonna use table N, which is the one right before. And we'll see those in this unit here. But types of nuclear particles or decay particles that can be formed, these are the main ones in terms of things that we're gonna talk about posing a problem or posing an issue, or they're commonly found or discovered or released. First thing is alpha particles. All right, alpha meaning the Greek letter. If you know the symbol for alpha, all right, it looks like this thing right here. It's kind of a funky A. All right, I call it a squished fish. If you know that fish symbol, all right, it's kind of squished down. that can also be represented as a 4/2 He, which is basically a helium nucleus. It's a helium with no electrons left around. And then on your reference table, just to show you, you'll see that alpha particle is 4/2 He, or they'll put 4/2 alpha. Remember, these numbers are important. The top number is the mass number, which is the protons plus the neutrons. The bottom number is the atomic number, which is just the number of protons. All right, we're going to go into the strength or penetrating ability, just kind of pushing this here now. Alpha particles are a pretty big particle. So if you think of like a strainer, big particles don't get through strainers because they're physically too big. All right, alpha particles are weak because they are such a big particle. All right, they're going to get stopped by lots of materials, so they don't get through very much. All right, a beta particle is the beta symbol, which is this thing. All right, and betas have a negative charge. All right, alpha particles, one thing, because it's just a nucleus, one thing I didn't go over here, it has a +2 charge. So we've got 2 protons and 2 neutrons, so it's a +2 charge. The beta particle has a -1 charge. A beta particle is basically a high-speed electron. All right, and its penetrating power is a little bit, it's what we would call medium. It's relative, and I'll talk about what stops it in the next slide. But comparatively speaking, a beta particle will go through more things than an alpha particle because a beta particle is much smaller. Think of like the holes in a strainer. Smaller particles get through. All right, a positron, I know we haven't talked about these things, but they're basically a positive electron. Not going to really go into how they are formed. It's from the disintegration of a neutron, but that's something for your physics or higher level chemistry, more likely physics. Basically, betas and positrons have a mass of 0. All right, so that represents they're an electron. The difference being a beta particle is a -1 and a positron is a +1. All right, penetrating power for a positron is similar to a beta because it's the same type of particle. All right, it's the same size, so to speak. All right, and then we get down to gamma. Gammas make the Hulk. If you guys have watched it, what is it called? The Avengers. All right, that's how gammas were. That's how the Hulk was made. All right, gammas aren't a particle. They're actually a wave of energy. All right, so that means waves can go through things. So their penetrating power is very high. All right, it's very high. It can go through lots of things. All right, think about if you've ever had an x-ray, they put that lead shield on you. And think about what parts they're covering when they do that. All right, they're covering reproductive parts. They're covering parts that have cells that are rapidly dividing. They really don't worry about your brain getting radiation because your brain really isn't going to be affected by it unless it's a really high form of ionizing radiation. Because your brain cells are already formed, you're not going to make any more. But they cover up your reproductive parts because those things are rapidly dividing. And in some cases, your bone marrow and your body too, because that's rapidly dividing as well. All right, so those are the major particles. All right, we'll go through a couple more real quick, but I wanted to show you table O here. So here they give you the symbols for alpha particles. They give you the symbols in alpha. All right, beta, they give you the numbers, and they give you what the beta symbol is. All right, gamma, 0, 0, and then the symbol is that it's a funky Y is kind of the way I talk about it. We will deal with neutrons in here, which neutrons aren't new to us. They don't have any protons, so the bottom number is 0. Their mass number is 1, so it's 1/0. All right, our proton is 1/1, which is basically a hydrogen nucleus, hydrogen right here. Or sometimes, this is a very old notation, 1/1p, which I haven't seen at the Regents level in a long time, so I think they're phasing that out, thankfully. And then a positron, like we said before, is just a positive electron. All right, we're going to see this. Now, this is a table. Unfortunately, if I made it so that you could see the whole table at once, you wouldn't have been able to see it on the screen. So I clipped it so it's in 2. But basically what I want to show you is like if they give you a nucleus or an element over here, or at the bottom half of the chart over here, you can look on here and see what its decay mode is. And that's going to become helpful when we start writing decay reactions, which we're going to do in a minute here. All right, so you don't have to memorize any of these things. All right, you just, if they say that you want what's the decay series for iodine 131, you look on here for iodine. You have to know your symbols, which is I. Iodine 131 is going to give off a beta particle. So on here, if you look at it, they got beta particles, they got positrons, and they've got alphas. That's all they're dealing with here. They give you the half-lives of these things, which we will talk about in a later lesson, not today. All right, these are in alpha order. It's got to be by symbol, all right, not by name. All right, because gold AU, so it's alpha order. If you're trying to find something on here, go by alphabetical order of the symbol. So it just kind of helps you find it a little bit quicker. All right, so back what I said before, we're going to show you the penetrating ability. So alpha particle, because it's a big particle, is going to get stopped by pretty much anything. Even a couple feet of air will stop an alpha particle. That's the type of radiation that's in a smoke detector. All right, so that's why we're not really impacted by that. So paper will stop it. Beta needs a little piece of metal. All right, not too thick. All right, it tells you down here 0.5 centimeters of lead, and that's if you're getting immediately bombarded with the beta particles. Even air, you know, I think it's like 10 feet of air or something. I forget what the correlation is to stop beta particle. Then gamma, good luck. All right, you need 10 centimeters of lead, which is a couple feet of lead. All right, so you need pretty big shielding. You know, when you get to a nuclear reactor, I think, what is it, like 10 or 15 feet of concrete, and then they'll have like, you know, 5 or 10 feet of lead shielding just to protect the core from any of the radioactive materials getting out of the core in there. So that's penetrating ability. Alpha, it goes just in order. Alpha gets stopped easiest, then beta, then gamma goes through the most. All right, so here we go. Other particles, neutron, 1 over 0 n, which we saw before on table O. A positron is a positive electron. We've already seen that. I put that here again, though, just because terminology, like, I need you to see it multiple times. And then proton, all right, which is a hydrogen 1 or a hydrogen 1 atom, or nucleus, which is 1 over 1 H. All right, here we go. Alpha emitters. So here's we're going to wrap up with just writing emission reactions. All right, so you've got Ra-226-88. Now, I think this is on your reference tables, but I'm telling you it's an alpha particle or alpha emitter, but you could look on your table N and see that it is. So we're going to write it. So on the product side, on the other side of the arrow, we're going to write 4 over 2 alpha. Now what we have to do is we have to predict there's a missing particle here. And this is where simple math comes into play. You have your arrow. Your arrow is your equal sign. All right, the bottom number here, the bottom numbers on the left have to add up to equal the bottom numbers on the right. So here, since we only have one thing on the left, it's 88. So over here we have a 2. All right, so what's going to be the atomic number of the missing particle here? What plus 2 equals 88? So what plus 2 equals 88? I think everybody knows 86 plus 2. So our missing particle is going to have an atomic number of 86. All right, our mass number works the same way. So what plus 4 equals 226? What plus 4 equals 226 is 222. So we have 222 over 86. Now what we have to figure out is what element is that talking about? So we have, do we look at the top number or the bottom number? You always use the atomic number or the bottom number to figure out what the symbol is going to be. So since our missing symbol is 86, we look on here for atomic number 86. All right, number 86 is Rn. So Ra will turn into 222 over 86 Rn. So that would be what's called our daughter nucleus. The sum of the bottoms, the sum of the atomic numbers on the right, have to equal the sum of the atomic numbers on the left. All right, we look down here. So I'm going to go quickly. I know you can stop and write, so I'm going to try to go quickly to make this video as short as possible. Here we got U-238. All right, you can look on table N, or I'm telling you that it's an alpha emitter, so it's going to give off an alpha particle, and we have to figure out what its daughter nucleus is, all right, or what it's going to evolve into. We know the mass number of the missing particle is going to be something plus 4 equals 238, which is going to make it 234, which doesn't really help us a whole heck of a lot in figuring out the missing particle. All right, but we do need that number. But what we do need to figure out is what is the number for uranium. Where do you know the number for uranium? You look on your periodic table. Uranium is down here. Uranium is number 92. So our missing particle is 92, or not our missing particle, the missing atomic number is 92. So now we can figure out the atomic number of our missing particle. What plus 2 equals 92? All right, what plus 2 equals 92 is number 90. All right, so once again, you look on your periodic table, you find atomic number 90. Atomic number 90 is down here at the bottom, which is TH. So the daughter nucleus for this is going to be 234, or thorium-234. This would be radon-222. All right, radium-226, so radium-226 transmutated into radon-222. All right, that's kind of how it reads in like what you would call an English statement, so to speak. All right, and then uranium-238 would decay into thorium-234. So that's writing alpha emission reactions, which is what you're going to have to do for homework tonight. All right, so remember the sum of the tops on the right equal the sum of the tops on the left, and vice versa. Okay, beta emissions. So beta particles. So I'm going to tell you these things are beta emitters. So here we go. We got uranium-239. Notice uranium-238, uranium-239. They are different nucleuses. All right, they are radioactive because they are above 92 or 82. All right, so but they're not going to all decay the same way. So uranium-239 is going to give off a beta particle. Beta particle looks like this: 0 over -1b. Now, this is the most challenging math for some people in this unit because now we have to figure out. Now the mass number is easy. What plus 0 equals 239? So the missing mass number is 239. The atomic number, you got -1. What plus -1 equals 92? So if I do, a lot of people try to jump at 91. 91 plus a -1 does not equal 92. 91 plus a -1 would equal 90. So our missing particle's got to be 93. So 239 over 93, and then you look on your periodic table and you get NP as the symbol for that. Don't use the top number to get the symbol. Use the bottom number only, and that's neptunium. So uranium-239 will decompose into neptunium-239. All right, our other next beta emission reaction, just like before, we didn't write down the atomic number. A lot of times it's redundant. If we know the symbol, then they assume that you can figure out the atomic number by looking it up on the periodic table. All right, but this is going to be a beta emitter, so we can give off a beta particle. All right, gives off a beta particle. All right, and then we got to figure out what the number of P is. All right, so P, if you look, P is right here. What number is P? P is 15. So atomic number 15, and then so our missing mass, the mass of our missing particle is 32. The atomic number, so what plus -1 equals 15? 16 plus -1 equals 15. So our missing particle in this case, because it's atomic number 16, is a sulfur atom. So phosphorus 32 will decompose into sulfur 32. Okay, and that's a beta emitter. All right, these are the videos that I'm going to put links for on the website. All right, most radioactive ones, and the Marie Curie one is the two big ones. Uses of radiation is another one. And then I'll put a crash course, I can't say that 5 times fast, on what is radiation. It does help to explain, where you can see radiation in other places. It goes a little bit more into detail than I did. Okay, all right, so that's it for today. I'm scrolling back to show you homework. Homework is to watch the videos and pages 4, 5, and 8 in the packet that I'm going to give to you guys. All right, remember, if you don't have a printer, then you have to write out the entire reaction because I can't just go from one particle. I have to see the whole reaction, which isn't that bad, but just so you know, that's what you got to do. All right, we'll see you guys. Have a great weekend. Stay safe.